Okay, hello everyone. First of all, I have to apologize with the locals. I mentioned this, and I wanted to put some reference to Copenhagen in the picture, but not like an apocalyptic scenario where it was going to an AGM. But today I'm here to talk about heavy neutral leptons and how we can search for them in KM3NeT-ORCA. Okay, so I guess Arif made a lot of work for me, and he actually explained what is KM3NeT. That is actually not only one detector, but two different detectors, KM3NeT-ORCA and KM3NeT-ARCA, one located in the south coast of France, and the other one, ARCA, in the south coast of Sicily. So they share the same technology, same data processing, same software, and same people working on them, but they have different sizes and granularities, and this is due to the different goal they were built for, right? So ARCA is intended to look for high energy neutrinos in the sub-TeV to few TeV range, to do mainly astrophysical studies. Also, although there are many others going on, and ORCA was intended to actually look for low energy neutrinos to study actually the fundamental properties mainly. As every good neutrino collaboration, we compare here the size of our detector with the Eiffel Tower, and we see that ARCA is way bigger. You see all the lines with these domes that are the optical modules deployed there that actually will detect the Cherenkov light. And it's a detector under construction, both of them. So here you see actually like the zenithal view of both detectors, and in like light colors you see the DUs that are actually the lines that are already deployed. So for ORCA we have 28, and for ARCA we have 33. I think even if we are now in sea operation, so we will see at the end of this talk. You also saw this plot yesterday in the same presentation. I'm going to work with KM3NeT-ORCA that has already this lifetime that you can see in this y-axis. Here in the x-axis is the date. And I'm going to actually study if we can actually look for these heavy neutral leptons that Marian presented in the configuration ORCA 18. So just in case you haven't seen one, this is a heavy neutral lepton underwater, according to ChatGPT. But it is also, as Marian mentioned, some BSM extensions, or some extension of the standard model, due to the fact that neutrino oscillate, so they have masses and they are tiny, and that's not fully understood. So if you add some right-handed neutrinos to the standard model, you can actually, through this CISO type 1 mechanism that she explained, actually miss them and suppress the mass of the light standard model neutrinos and get something reasonable. So there's a plethora of models of heavy neutral leptons, some of them with masses on the kilo electron volt range that could be actually their matter candidates. Otherwise in the GeV range that has successfully generated matter-antimatter asymmetry. But what you have to take into account is that they are theorized to be right-handed neutrino partners with high masses and with feeble interactions with the standard model. So there are different portals where you can actually get from a neutrino this heavy neutral cousin. This is the one that they mentioned, the CISO type 1, where it actually mixes with the neutrino and with a fixed field, and you would get this right-handed neutrino. But those cases are quite studied, and we are not that sensitive to it. So I'm going to focus on this specific case, that is the dipole portal model, which with a photon as a mediator, you can actually get from a neutrino a heavy neutral lepton. You can see more details in this talk. I will not go a lot into it. But what is cool is you can actually detect the presence of these heavy neutral leptons in ARCA. What you see here is a bunch of hits, that is like the detection of the PMTs, and then in a second shower some other hits. Why? Because what would happen is that a neutrino would actually interact and upscatter into this heavy neutral lepton that doesn't have a very long lifetime. So it will travel, you can actually not see this travel, and it will decay emitting a photon, and then you would get a second shower of light. So you will have two showers of light separated a certain distance. That is what the signal that we are actually looking for. So of course I'm not that intelligent. It's not the first time someone has looked into it, and of course there's I don't know if you have heard about, but there's a detector in the South Pole that is actually very similar to ours, and they have already looked into this. The name is IceCube, but they have a problem that is, well, not a problem, an advantage, but actually a difference, and is that the detector is in ice and our detector is in water. So due to ice properties, the scattering of the photons in ice is is way bigger than here in water. So for the same event, you can actually get maybe in water worse energy reconstruction, but actually topologically, you can actually get some improvement. So some of the preliminary results to this, what we wanted to do, or what we have done, is actually with the Harvard group, that they developed this software called Siren. We simulated some of these double bang events in our detector, and then we did like a pipeline to actually try to get rid of all the background that we can have. That is not only in this case noise and muons, but also neutrinos, right? So that's a very fine-tuning problem, and even if we are very good at getting rid of muons and noise, then it was quite subtle to actually get these side channels, and we've used a modification of particle net model that is a model developed for LHC to actually look for jets, and with some fine-tuning of it, we actually saw quite good performance. So we actually, from this mini boom paper that I haven't referenced, I'm so sorry, but I will in the future. We have actually looked in this parameter space that is the mass of the heavy neutral lepton, and this dipole moment mediator that actually accounts for how alike is that a neutrino will actually produce a heavy neutral lepton. You can actually explore this phase space with different points. Some of them are ruled out, but we wanted to see how many events we expect. And we see that for a couple of models, we actually expect for showers with more than 10 meters separation in cascades. That is something we can see. We expect order 33 or 14 events. So it's very nice per year. And our capacity to distinguish them actually relies on this pipeline that is first like some cuts to actually get good events, then some consecutive BDTs to get rid of muons and noise, and then one anti-neutrino cut to actually just find a H-channel sample. So fairly easy for muons and for noise. You can actually get rid of almost all of them while keeping quite a considerable neutrino sample, and also H-channels cluster similar to neutrinos. So that was very nice because you keep most of them. And then also the capacity to distinguish between neutrino and heavy neutral leptons, it's quite remarkable. So we could get a very nice and pure sample of heavy neutral leptons. Here you have the different levels. These are the heavy neutral leptons, these are the neutrinos. And you see that in the final step, you can get rid of almost all of them while keeping a considerable fraction of heavy neutral leptons. So in this case, with scenario, we were able to achieve 5 events per year in a very clean sample, which is kind of remarkable, even if it's quite preliminary and of course already ruled out model. But yeah, this brings me to my conclusions that are very promising results, but are still very early phase. So hope you keep tuned, and thank you for your attention.
Thank you, Jorge. I guess these double banks that you have, I mean, there could also be some overlap with some standard model channels, like for example, the tau.
Yeah, there's a fundamental reason that you are looking for the low GeV range. So tau neutrinos will have a separation of millimeters, while these have separation of order 10 meters or up to 100.
Yeah. Okay. So way to
there's
distinguish.
Very no background. I mean, we have to check the background with two muons entering the detector, like these muon bundles or whatever that could actually cause a fake signal.
How good do you need angular resolution as well, or is it just that you at some time see these two cascades in ORCA?
You mean for the...
Yeah, do you need also angular reconstructions for the cascades?
Yeah, we need angular reconstructions, and actually one thing that has proven quite capable is if you, for very low energy events, you actually have a shifted angle between the second cascade and the first one. And the GNN is actually capable of steering a little bit. Okay. So with those non-linearity, you can actually achieve also some very nice results. Yeah.
Okay, are there more questions?
People are tired.
Okay, thank you very much, Paul.
Thank you.